great. Now I am going to switch to the crown jewel of boundary value problems. And as we finish off, I'll finish as much as I can today, and we'll continue next week. And all right, so I'm giving you now, it's same heat transfer problem. I fixed the boundary conditions at the left and on the right. We could put Newman conditions, and you should be able to know how to do that after you review the slides. But what I changed here is the right-hand side. Rather than having t minus t infinity, now I have t to the fourth minus t infinity to the fourth. That's the equivalent of the radiative heat transfer initial value problem we did with the lobster. Now we're cooking the rod in an oven, okay? But we're looking at the distribution of the heat inside the rod. So now take the lobster and think it's at steady state, okay? And assume the lobster is this rod, okay? And then we're gonna look at how the temperature changes inside the lobster as it's exposed to this heating environment. So now I'm gonna ask you to take a couple of minutes to discretize this equation at an arbitrary point I, okay, in the domain, inside the domain, interior point, t left and t1 and tn, they're t left and t right, so you know the equations there. What's left is everything in the middle. So I want you to discretize this equation at point I in terms of I minus 1, I plus 1, etc. And write it in matrix form or make a comment on what you observe, okay? While I eat a gummy bear that my son left me on my lap. Okay, time. All right. Let's see. Brendan, do you have an answer for us?
Like an answer is in what do I observe, or the
both. What is the discretized equation and what do you observe?
So if I'm understanding correctly, it'd be like u minus I minus 1, or I guess, sorry, t I minus 1 plus 2t plus t I plus 1 equals.
So minus 2ti, not plus 2ti.
Oh, whoops.
Minus 2ti. Yeah, ti minus 1 minus 2ti plus ti plus 1 over delta x squared, right? So that's, yeah, okay.
Yeah, and then equals the right-hand side, so alpha times t to the fourth minus t infinity to the fourth.
Okay, t to the, which t? At what point? So remember, now we're discrete.
Yeah, ti.
Okay, so this formula, right?
Yeah.
Okay.
And so, I mean, my observation was just that that looks a lot like Euler's formula, but like for a second derivative.
So what is Euler's formula?
So it's our current guess plus the delta x times.
Okay. So I know what you're alluding to, but there's another way to phrase it, and you got to be careful about how you're describing this. Okay. So I'm gonna ask if someone else has a comment. So far, Brendan is correct. This is the equation, and I hope this is the equation you were able to obtain. Okay, by now you should be able to know how to do this. All right, so let's see. What other observation can we make? Andy, are you with us? There's a very important observation we make here. I mean, this is just the heat equation, right? So can we just solve this?
Yeah, I'm here.
Yeah.
Personally, I don't really have any observations on this.
Okay. So then we can just put this in a linear system, just like we did matrix vector and solve it.
Well, Ti on the right-hand side shows up non-linearly.
Okay, so Paul, yes, that's right. So Paul and Salim, they're both saying that as well. And if you can't see this, you should be able to see it. This is a nonlinear term. So previously, when we did t minus t infinity, everything showed up linearly, and we were able to turn all the discretized equations at all the points into a linear system of equations. However, this is a nonlinear equation because we are solving for ti and ti minus 1 and ti plus 1. And ti shows up nonlinearly over here. And if you were trying, are you guys still hearing me? Yes. And if you're trying, hello? Hello? Okay, great. There was some internet connectivity issues. Can you hear me now?
Yep.
Okay. All right, so this is a nonlinear equation, all right? So we can just put it in a, just put it in a linear system, tridiagonal system and solve it because it's a nonlinear equation. And if you cannot see it, actually this is a system of nonlinear equations because at every point, except the T1 and Tn, at every point, you have a nonlinear equation that is coupled to a nonlinear equation at the neighboring points. So the equation at Ti is coupled to Ti minus 1 and Ti plus 1. And the equation at Ti plus 1 is coupled at Ti minus 1 and Ti and Ti plus 2 and so on. And they all show up nonlinearly. Now, we did cover systems of nonlinear equations, right? If you remember Newton's method. And we know how to solve this in principle, but can you imagine having 2,000 of these equations? Can you imagine the size of the Jacobian and how annoying that is going to be? I mean, it was one thing doing a system of 2 or 3 nonlinear equations, and that was annoying enough. But can you imagine doing this for a problem like this? It's going to be very, very expensive. Okay, we can do it. We know how to solve this using Newton's method. Okay, so this is a system of nonlinear equations that we have to iterate through, using guesses, etc. We would linearize it, etc., and solve it. But left untouched, it is very impractical. Left as is, it's very impractical to solve. Okay, and I probably have 30 seconds left, but there's a way to avoid the nonlinear solver. And what we're going to do next Tuesday, rather than having to do a Newton's method on all of this, what we're going to do, we're going to embed the Newton's method. Whatever that means, doesn't mean anything to you now. You'll see what we're going to do. We're going to embed, we're going to take the right-hand side, the nonlinear right-hand side, linearize it, and then iterate the entire system of equations as if we're doing Newton's method, but without doing Newton's method. It's much easier and much cleaner, okay? But what you should take from this is identify that this is a system of nonlinear equations, okay? Not a single, just nonlinear equation. At every point I, you have a nonlinear equation that's coupled to the other ones, and that gives you a large system of nonlinear equations. And with that, I will let you go. We will finish this off next week. I'll repeat what I announced early on. Make sure you go.
Professor?
Yes.
So the final exam is from 1 to 3 Mountain Daylight Time.
Yes,
right?
yes, our time. Yep.
Okay.
If
because I'm in Arizona, so it's an hour earlier.
Oh,
so
you gotta be.
12 to
Yeah.
2,
Yeah.
Right? Okay.
I think so. I'm challenged with time zones because I grew up in a single time zone place. So this time zone thing is confusing to me. But yes, so make sure you, it is Mountain Time. Okay.
Okay.
It is Mountain Time. Yeah, thank you. Okay. All right. So last time we did a boundary value problem. It had a kind of benign right-hand side. It was a heat transfer in a rod, and we understood how we discretized that, converted at each, discretized this into points, discretized the rod into discrete points, and then converted the continuous ordinary differential equation into an algebraic relation that relates, you know, the unknown temperature at one point to the unknown temperature at two other points, but that gave us a system of n equations with n unknowns, n being the number of points, and then we know how to solve that. We can use NumPy solve, etc. That's not an issue. But then we looked at this boundary value problem where I only changed the right-hand side. Previously on the right-hand side, you had something, a function of the temperature t only, not t squared or square root of t or sine t. And then I asked you to discretize this, and you all went ahead and discretized it correctly. But then you observed that the discrete equation at every point is actually a nonlinear equation. So the system of equations that we're going to build is going to be nonlinear in this case. And we discussed that at length last time. But just to remind you, we are trying to solve for ti, for I going from 1 to n, right? And every equation at every point is coupled to all the other points. So you need, they're coupled. So that means you have a system. Okay, so equation 1 needs equation 2 needs equation 3, and so on all the way to the n, point n. But each one of those equations is nonlinear. And I said that if left untouched, this is a very large system of coupled nonlinear equations. Can we solve it using Newton's method for systems of equations? Absolutely. But it is very expensive to do. Okay, so what I'm going to present here to you is the last thing we're going to cover in this class, and that only kind of works for differential equations. And we do this all the time in the research area I work in. We call this source term linearization. Turns out there's a way to embed the Newton solve within the system of equations that we obtain, rather than having to build a Jacobian, and the Jacobian matrix is annoying and huge and is very dense. So rather than having to do that, we kind of circumvent Newton's method and embed it within the solution process. And I'll explain that to you briefly today. It's called source term linearization. When the source term in a boundary value problem is nonlinear, this is what you can do. Now, for initial value problems, if the source term is nonlinear, you just use Newton's method, because with a initial value problem, you either have one equation or you have like 4 equations. Even if you have like 50, that's nothing, right? So you just use Newton's method for an implicit method. So remember, with initial value problems, if the right-hand side of the equation is nonlinear, you'll only get a nonlinear equation if the method is implicit. If the method is explicit, it doesn't matter, because you're using values from the previous time step. All right, so for boundary value problems, what I'm going to do here, I'm going to split the screen in 2 portions. On the left-hand side, I'm going to describe the general form, but on the right-hand side, I'm going to do it for a very specific example, which is the one we just described. So in general, if an ODE is given, and I'm giving one specific example here, d2u by dx squared. You could have d2u by dx squared plus du by dx, right? Doesn't matter, you just discretize that as usual, but what matters is the source term on the right-hand side, if it's nonlinear or not. So in general, fxu is nonlinear. And on the right-hand side, I'm giving you a specific example. In this case, the nonlinear source term is alpha t squared t to the 4th minus t infinity to the 4th. Now, t infinity is a known quantity, so that's not the nonlinear term. The nonlinear term is t to the 4th, okay? That's, it's nonlinear in t, okay? All right, so the first thing we're going to do, we're going to start with a guess for the solution for u. Now, this is similar to what we did in Newton's method. We had a nonlinear equation. We would start with a guess for the root and then refine that guess until we hit the root, right? So this is no different. We're going to apply that same method to the equation directly, to the full continuous equation directly. So we're going to assume a guess. star. It could be the initial condition for the problem, or one of the boundary conditions, for example. For in this case, could be the boundary condition, one of the boundary conditions, t left or t right, for example. Call it u star. For our example, we're going to call this t star. Then we're going to write the Taylor series of the source term around u star. Now remember, the Taylor series was our preferred method to linearize a nonlinear equation, and that's what we're going to do here. So if the source term in general is f of xu, you're writing the Taylor series around u star, so you're only taking derivatives with respect to u, not with respect to x, okay? Pardon me. So you get fx at u star plus u minus u star df by du. You're differentiating with respect to u, right? At u star and so on and so forth. Now for our specific problem here, specific example, we don't have x in the right-hand side, so our source term is only a function of t, and this would be the Taylor series, and this is gonna give you, oh, sorry, I missed one thing here. Okay, now we write the Taylor series, we're gonna truncate at first order. So we're gonna keep the 0th order term and the term that has the first derivative. So those are the first terms that we're gonna keep, like we did with Newton's method. And this gives us your first activity. Now I want you to write down the Taylor series for f of t for our specific example. Our example is f of t is alpha t to the 4th minus t infinity to the 4th. So go ahead and write the first two terms in the Taylor series, or up to first order. Okay, you got 2 minutes. Okay, let's see. Katie, since you are in a different time zone, do you have an answer for us?
I believe so.
Okay, go ahead.
Do you want it for the specific example that we're doing?
Yes, for our specific example, yeah.
So I wrote it down as alpha times t star to the 4th minus t infinity to the 4th.
Correct.
Plus, in parentheses, t minus t star. And then that multiplied by 4 alpha t star cubed.
Excellent.
Minus t infinity.
No, there's no t infinity because t infinity is not a function of t, it's a constant.
Right.
So
right, that would go to 0.
Okay, so 90% correct. Okay, so what Katie said is correct. We linearize our full source term, which is alpha, over here, alpha t to the 4th minus t infinity to the 4th, by taking the first two terms of the Taylor series. We're committing an error, but we're not going to worry about that because we're only going to approximate, we're going to iterate through this until we find the root. Now, if you haven't seen this already, what I'm trying to do here is, my goal is to refine t star until it is consistent with t, the true solution, or the root of the equation. Remember, our t star is the guess, and t is going to be our actual solution, our actual root. So initially, they're going to be different, and we'll see this in a second. But the first step is to take this full source term and approximate it, linearize it. Now, all terms are linear because t shows up linearly, And T star is just like T infinity. It's a guess, okay, that we're gonna keep refining until we hit a certain condition. So I would typically just simplify the algebra like I'm showing here. So my full source term becomes minus 3 alpha T star to the fourth plus 4 alpha T star cubed times T minus alpha T infinity to the fourth. Again, T is our unknown, okay? And T star is only a guess. That's why there's no nonlinearity over here anymore in terms of T. Everything is linear in terms of T, as long as we know T star, okay? And T star is a guess, and we're gonna refine it. We'll see in a second. Now we substitute into the ODE. So you take the right-hand side that you just derived. Again, on the left, I'm showing the generalization, which I think, you know, could be too much for someone to kind of memorize or reproduce. Just do, if you follow the steps, linearize the source term, substitute into the ODE, just follow the steps, you'll be able to apply this to any type of ODE, okay? Don't blindly use the general formula, okay? And so we substitute into the ODE, and now I claim that this is gonna be our new ODE that we're gonna be dealing with. Remember, we're still continuous here. We haven't discretized anything. All we did was approximate the source term around some guess T star, okay? Next, we discretize our standard discretization, and that gives us the standard central discretization on the left, and on the right, everything is at point I. Now, there's a trick here, not a trick, there's a subtlety here that T star is not a value across the entire domain like T infinity. Every point in the domain has its own T star. Again, think of T star as the guess for the root of the nonlinear equation at point I. And therefore, every point I has a different equation and therefore has a different root. Therefore, your guess needs to be a vector of guesses, right? Rather than just one guess for the entire one constant value. Every point has a different guess, has a different root, okay? Because it has a different equation, different nonlinear equation, okay? Next, we collect the terms. We put everything we don't know on the left-hand side, all the unknowns on the left-hand side, and everything we know on the right-hand side. It's just algebra. So, you know, if I were you, I would derive these equations at home and make sure that, you know, you collect the terms, everything correctly. So now, pardon me, we actually have a linear system of equations, right? So at point I, the linear equation is given by Ti minus 1 minus 2 minus into 2 plus 4 alpha delta x squared, etc. Ti plus 1 minus alpha delta x squared into whatever. Again, our unknowns are Ti's, so Ti minus 1, Ti, and Ti plus 1, and that gives you a system of equations, okay? And these equations are linear. So in the general case, I'm showing the matrix on top. Again, don't worry about that. Worry about doing it specifically for a particular problem. So for our particular example, this would be the system of equations. It's just nothing different than what we did before, except we have this annoying T star or U star floating around. Okay, so now we can, given a value for T star, you can solve this system, agreed? Because the coefficient matrix is known, there's actual values in it. The only unknowns are the Ti's, T1 all the way to Tn, okay? But there's this U star everywhere. And we said that U star is only a guess for the true value of U, or T star is the guess for the true value of T, or whatever variable. However, we also know that U star should eventually converge to U. So U and U star need to be the same value, okay? However, when we are starting, we start with a guess U star, and then we solve for U, or we start with a guess for T star, and then we solve the linear system for T. But then they're different, right? U star, T star, and T are gonna be different because in general, you're not gonna be able to guess the true solution directly, right? So what do? We just iterate. So we first start with a guess for our solution, this T star or U star at every point, okay? And then we solve the linear system of equations, okay? And to solve that, you need to use U star in the coefficient matrix and in the right-hand side. There's U star everywhere, okay? So you update your coefficient matrix and you update your right-hand side. So this is more programmatic now, okay? What we do in terms of programming. Then you solve the system of equations for UI, and then you ask yourself, or TI, is t equal at every point? How far away are t and t star? If they're far, what do? You take the t that you solved for and make it your new guess and repeat until they all become close to each other, until u star is close to u or t star is close to t. And then you'd say, well, that's it. My guess and my solution have converged to the same value. And typically, these methods converge all the time, because this is another way of doing Newton's method, except we embedded everything in the system of equations, okay, rather than having to do a Jacobian, etc. Okay, and that's it. That's how you do boundary value problems with nonlinear source terms. I know it can be complicated to untangle all of these systems of equations and nonlinear and linear, and I understand, and it takes time. Okay, it takes time to kind of for this to sit in your mind, to stick in your head. But think always about what you're solving for. Okay, and over here we're solving for the u's or the t. Okay, and t star is only a guess that is given to you initially. You start with that, you solve for t, and then you say, well, my t star needs to be close to t. If they're not close, then I'm going to use my t as my new guess and repeat. Update the coefficient matrix, update the right-hand side, solve the linear system, and repeat and repeat. And in the remaining slides, I repeat this example for you that we kind of just did together. So make sure you go through it, okay? Because this will be on your final exam. So here's a tip for you. There's not going to be programming where you're not going to, in the homework that I gave you, there was a programming question to program this. And the programming this is very easy. You just embed the linear system, which we know how to build. We know how to build the coefficient matrix for this problem. We know how to build the right-hand side. So you embed those in a loop, and you keep looping until t star and t are less than a certain tolerance. And that actually concludes everything I wanted to cover in the course. Typically, I also go over partial differential equations, but we'll see if we have time by the end of the lecture. I'll go over those, but I don't think they should be required in this course at this time. And if you have any questions, go ahead before we get started on our activities. No questions? Okay, let me check the chat. There's no chat. Okay, I'm gonna go ahead and stop the recording because